Hello everyone, this is the Module 6 instructor presentation where I'm going to go over the major themes and concepts of Module 6, which is the perception of size and depth. This is from Chapter 10 of the text. So let's begin. So these are just some of the themes and concepts we'll be going through here. This is not an exhaustive list, but I tried to make them general enough to more or less fit everything. One point that you should be aware of is that the perception of size and depth are connected. You can't really have one without the other, at least not. You'll see that the two are connected. In other words, depth is more involved with how far away or how close we think something is. And of course, the size of an object is our estimation of, well, how big or small it is. We do need two eyes for the best sense of depth. I always like to point out that you can have a sense of depth with one eye, and it can be fairly good, but two eyes we'll see really gives it almost, it's sort of analogous to mono versus stereo sound. Stereo sound is quite a bit richer and fuller than mono, and that's because stereo relies on two ears, just like 3D depth perception relies on two eyes. One of the issues we'll also mention here that's kind of like, we always have to try to figure out certain questions that need to be addressed, before was the binding problem with vision and other, and so forth. Here's the correspondence problem. And this is essentially that we have, this will make more sense in a moment here, but essentially we need two eyes for depth, and how does the brain sort of reconcile both of these images that we each get from each eye, essentially. We'll see each eye gets its own image, essentially. You need to be aware of all the various cues that create a sense of depth. There's cues that rely on one eye and cues that rely on two. And lastly, this is something that I keep saying now over and over. Our perceptions are the result of our nervous system. What we experience is not exactly what the reality is. And, I have some and this is revealed by illusions and so forth and some other things. And I have some really good video clips for you to look at as well on the website. But once again, I want to kind of go against this notion of naive realism that we are experiencing the universe exactly as it is. I'm not saying that, I keep making this point. I'm not saying that what we're experiencing is completely and totally subjective and is totally divorced from reality. It's not, I don't think. But we have to account for the fact that our nervous system, the way it works, the way our brain works, the way our sensory system works, has a huge impact on how we perceive the world. Okay, so also as I go through this, I'm not going to necessarily go through every one of these slides in detail. I'm just going to sometimes I might just point some things out to take note of, but I do want to maybe mention various things, and some things I will spend some more time on. Perceiving depth, be aware, of course, the cue approach. All right. We start off with the retinal image. That's the beginning point. But as you will see, that alone cannot explain that retinal image that we get on both of our eyes is not sufficient to explain the perception of depth and size, just like it wasn't sufficient to explain color. It's the same thing here. So the cue approach does focus on that retinal image to a certain extent. So as you go through the readings, just make sure you pay attention to what all the different cues are and so forth. But here you can see an example. These what this point here is that this two-dimensional image alone does not really convey a sense of depth. So somehow our brain has to figure this out, so to speak. Somehow our mind has to figure this out. So the image on the retina alone is not sufficient. Okay, and so we go through various cues, and then there's oculomotor, which includes convergence and accommodation. These are cues based on our the positioning of our eyes, muscle tension of the eyes, and so forth. There's convergence and accommodation, and you can see an example of convergence there. Close objects tend to make the eyes converge. When we look at distant objects, our eyes tend to diverge, and that can serve as a cue for how close or how far something is. We also have monocular cues, which are cues that rely on only one eye. Now, these cues allow us, sometimes they're called, a subset, we can call them, or pictorial cues. When we look at images, paintings, pictures, movies, unless they're a 3D movie, we're relying on two-dimensional images to get a sense of depth. All right, now And so there's lots of, and the text has a lot of images that you can look at, and a lot of artists, if they really want to convey a sense of depth in an image, they can utilize these cues. And in movies, for example, a lot of in particular, if it's a special effects heavy movie, they've got to create at times a sense of depth to maybe make that scene work a little better for the audience. But unless they're using 3D, they're largely having to rely on two-dimensional pictorial cues and so forth. And you can see there's occlusion, relative height, um, objects. You can see that you can see higher in the field of vision tend to look more distant. I don't think I could show this due to copyright, but the beginning, if you go on YouTube and watch the very beginning of the 1977 Star Wars movie, the original one, the first one that was made, that was released, I should say, back in 1977, the opening shot, which has become quite famous, where the Star Destroyer is that's the Empire chasing the Rebels, in the very, very beginning shot, the first couple of minutes, there are so many wonderful cues that are utilized, which include occlusion, relative height, all kinds of stuff in that image, to really get a great sense of depth without having to utilize 3D. And it's really, really impressive what they did. So I like to always tell my students that people in the special effects, that work in special effects, they probably have to be aware of these cues, at least sort of intuitively, to make it look right. All right, and there's other ones: relative size, perspective convergence. This is another one that's used in that opening scene if you watch it. Parallel lines appear to come together at distance. This is the so-called, if you look at railroad tracks going off in the distance, this will look like this. We utilize our memory, familiar size. Distance information is based on our knowledge of the objects and so forth. So we have what could be more of a bottom-up type processing going on here, but then our memories, our familiarity, learning effects, this could also be more of a top-down process. Atmospheric perspective, texture gradient, shadows, all of these things can be utilized. And like I said, in movies, also video games, of course, virtual reality, and all these other things. All of this stuff can be utilized so that we get a good sense of depth. Here you can see a painting. You can see here. There's a number of cues that are utilized here, right? There's occlusion, there's texture gradient. Here's the linear perspective. It gives the sense that this structure in the distance there is further away and so forth. So you can look at, if you go to an art museum and look at some of the paintings, especially scenes or whatever, any good artist, if they're trying to convey a sense of depth, they will create a painting that can utilize these cues to create a greater sense of depth. Here you see atmospheric perspective. Fog always makes things appear to be farther away. All right. And that's what's happening here in the shot. And there's a number of cues there. You can start guessing. The same thing with this image here. Here we have a texture gradient and so forth, all kinds of stuff, any number of cues. So, go through these different images. Like I said, you can even look at movies or whatever, especially special effects movies, and you could see how do they create a sense of depth with the cues? What kind of cues are really used a lot? Okay. Motion parallax is also something that can be utilized. This is utilized in video games. Close objects appear to go rapidly past you, whereas distant objects appear to move more slowly. This is also used effectively in the beginning of the 1977 Star Wars movie, very effectively. And so there's all kinds of stuff. It's really cool. And this is a nice little overview here of the different cues and generally how effective they are at different links from you, essentially. And so forth. For example, atmospheric perspective tends to work really well for distant objects and stuff like that. But all of these are really good. All of these cues can be utilized to increase the sense of depth. Now, those are great, and they can be, they can provide that depth. And once again, you only need one eye to do that. So you can, even if one of your eyes was not working, pictorial cues are just fine. Stereoscopic, though, is a much greater sense of depth, and this is utilizing two eyes. Okay, so we do have two eyes. And as it turns out, essentially, each eye, when you look at a image, or when you're looking about your room, looking at the computer, each eye, or the image produced from each eye is slightly different. All right. This is called retinal disparity, and it's mentioned here. There's binocular disparity and whatnot. So here you can see this would be an example of that. What you have here is each image here of this house taken from this left camera and this right camera are slightly different. Um, sometimes what I tell students in class is real simple. Just look at something in the room you're in it and open and close each eye alternatively, and you'll see what looks like a shifting image. And that's what's going on. Each is different. Now, somehow, this is the correspondence problem. The mind combines the two and to create this unified image, essentially. And that's the correspondence problem. How does it do that? And that's the question we don't know. But anyhow, this is called binocular disparity. And that's the difference in images from the two eyes. So make sure in your chapter you spend some time looking at that. And then the author goes into some of the mechanics here, the horopter and some other things. This is anytime you're focusing, as you focus about different objects in the environment, there's this imaginary sphere that passes through that point. We call this the horopter. And essentially, there are things that can fall in the visual scene. Some objects will fall behind that horopter, some will fall in front of it, and some will fall along it. And most things tend to produce disparity, though. Okay, objects that do not fall on that horopter, that imaginary line, they produce what are called non-corresponding points, and these make what we say disparate images. They're a little different, and that disparity apparently is a cue for depth, and that disparity, by the way, is utilized to create 3D movies. That's what the glasses are doing. Each of your eyes, when you watch a 3D movie with the glasses and the technology, you're getting a slightly different image to the right eye versus the left, and then your mind combines those, right? The visual system combines those, and that creates a greater sense of depth than using just the monocular cues alone. And anyhow, you can see this is what they're showing you here. There's that horopter. In this particular example, Julie here is falling along that. So anything that is in front of or behind the horopter would create a certain amount of disparity. In other words, the images on each eye would be a little different. Anything along the horopter, it's corresponding, and in which case each image is identical. Anyhow, look through that in the chapter there. And there is technology that is utilized that could exploit this. The stereoscope is one. One of the videos I have for you that covers autostereograms goes into this, by the way. So this is a great video. So that make sure you look at that. When I have it's actually I have a link for how autostereogram technology works, which was related to this. So be sure to watch that. But stereopsis, depth information provided by binocular disparity. Stereoscopes can utilize this. This is essentially, as a kid, we have what are called the ViewMasters, where you get a couple of each eye gets a slightly different, disparate image of the same scene, and it creates a sense of depth. Autostereograms do this as well, using a two-dimensional image, and it creates a sense of depth. But here, once again, there's that correspondence problem. How does the visual system mass images from the two eye? We don't quite know. These are some proposed ideas. Matches may be made by specific features of objects. We don't know. But that is a question that we want to concern ourselves with. And I want to, and this goes along with one of the objectives, one of the themes is that the visual system is essentially through these top-down mechanisms creating this sense of depth for us through, somehow we don't know how it's doing this. So the depth that we experience is obviously we're taking in information from the environment, and that's important, but that our perceptions are the result of how the nervous system works. And if we can figure that out, we can understand how, more precisely how the depth perception works. You also need to be aware of course, the physiology of depth perception. We do have cells throughout the visual system, in the visual cortex, for example, and whatnot, that tend to respond to different levels of disparity, right? So some images will produce greater disparity than others, but, and we do have neurons that respond to that, and neurons have been found that respond best to binocular disparity. These are called depth cells, and this was found using physiological studies, primarily with monkeys. So that's something to look at in the chapter. So binocular depth cells. It's kind of interesting, and here we see Blake, who did a lot of developmental perceptual work. If you disrupt this disparity, you can actually cause the cats that were used in his study to develop less binocular neurons. And you can see cats were reared by alternating vision between two eyes. They essentially would be raised where they had like maybe their left eye patched all the time or their right eye patched all the time and whatnot. So they basically didn't utilize, the cells were not getting information from the two, these depth cells are getting input from both the right and the left eye. And if you deprive them of that, you get an animal that essentially is not going to have binocular depth perception. So that animal will develop poor depth perception than animals reared normally. So that's sort of like a use it or lose it type of situation there. Also, what's also in your book, the DeAngelis study demonstrated with monkeys that essentially, once they isolated these depth cells, if they manipulate them physiologically, they can actually alter the perception of the monkeys. They can actually alter their three-dimensional perceptions essentially through the stimulation of the cells. So the actual activity of these the actual perception of these monkeys can be altered by stimulation of particular cells in the brain, in different parts of the visual system, which is interesting. Okay, so that's a little about depth. What about size? All right, distance and size perception are interrelated. All right, so this is one of the points I made earlier. We judge our visual system, at least the theory goes, is we'll judge the size of an object based on how far away we think it is. All right. We don't just utilize the image on the retina, although that is also used. All right. So one of the experiments that you need to be aware of in the text is one of the more important ones is the hallway, and that's what their name is, hallway and boring, and they used hallways as sort of kind of strange, but that's what happened here. Hallway and boring, and this is an old experiment back in the 1940s. It's essentially a psychophysical experiment. It's really good. Using humans, an elegant experiment. What hallway and boring were interested in is trying to figure out what they were thinking. Okay, we know that we understood back then that distance and size perceptions were interrelated, and they wanted to understand in a little more detail how exactly they interrelated. How is our estimation of an object's distance? How will it affect how big or small we think an object is? And they also were aware of something called the visual angle, which is explained in your book. And so let me kind of pull this up here if I can. This was in here. We see this is just the digital copy of your book. In your book, you can see an explanation of the so-called, here's the experiment here, of the visual angle. The visual angle, you can see the angle of an object relative to the observer's eye. All right, so that's essentially the visual angle is how, when you're looking at an object, how much of your retina is being stimulated by that object. The larger the visual angle, the more of your retina is being stimulated. The smaller the visual angle, the smaller amount of the retina is stimulated. So, one possibility is that, okay, well, we judge size simply by the how large the visual angle is. So, for example, if you're, say I'm using my laptop to make this, but if you're using your iPhone or iPad or you're using your computer to watch this, as you pull it closer to your face, visual angle gets bigger. All right. But one of the things, so that's true, but I also know when I pull this computer to my face, or if I'm pulling my iPhone to my face, I know that the iPhone itself is not getting larger. All right. So it can't just be visual angle alone. And they understood that. Maybe our mind is also taking into account the size of, taking into account how close or how far the object is. All right, and so they understood that. And basically, you can see the experiment here. In their setup, you can see a person sat in a chair looking at this comparison and test circles. They basically had to look at this comparison circle, which incidentally was one visual angle. And then the experimenters would move this test image closer or farther away. And what they did was they always made sure that the visual angle was the same here. So, it always casted the visual angle of 1. But note that the closer the image was, they had to make it smaller to keep the visual angle the same. If it got further away, they had to make the test circle larger. All right, now I want you to understand that under most conditions, we do not just use the visual angle to decide how big something is. We take into account the distance, all right? So bear that in mind. And this is the important feature of the test was that they all cast exactly the same size image on the retina. All right. So let me go back here. So what did they find? Basically, and then this is in your book. I'm kind of moving forward here. I will go back to the PowerPoint, then come back to this. And I've just explained that. So they on the trials they're told to adjust the diameter of the test circle to match it. What they did was they allowed, in certain conditions, to give, those various cues I was talking about, those monocular cues, the binocular disparity. They were allowed in some trials to have various depth cues available to them. And when you allow people to have various depth cues, our visual system is more able to accurately calculate the distance of something. All right, all of those different cues. And then as they progressed, they put them in conditions where they basically took away all the cues. All right, that's what they're showing here. All right, that's one. So here you can see the, and so going back here, what did they find? Well, when you give them depth cues, their estimation of the physical size of the circle is accurate. All right, this is, up here, basically the size, we know that as the distance increased, the size of the test circle was made to increase so that it can stay a visual angle of 1. So when you give people a good amount of visual cues, they can do this pretty well. But when you strip away the cues, they start to rely more and more on the visual angle alone. And then they made more and more errors in judging the size. All right, as simple as that. And so they relied more and more on the visual angle, in which case you can see back here again, looking at the image, kind of going up here. Note how the image gets smaller and smaller and so forth, but they can't really tell the difference anymore because they've lost those depth cues. So this experiment shows that we absolutely, in order to accurately judge the size of an object, we need to use those monocular cues. Ideally, we need to use binocular cues. Without it, we rely more and more on the visual angle. Just think if you've ever been up in a very tall building. I know this, I remember going up when I was a little boy, going to New York City, going up high on the Empire State Building. And then later, when I was a teenager, going up to the World Trade Center. Because back I remember visiting the World Trade Center. I must have been 18 or 19 years old, I guess, or maybe 17. I can't remember. This was like in 1987 or 88, something like that. And when there's a certain point when you reach higher and higher that all of a sudden all the cars and all the people below you, they don't look real anymore. They kind of look like little toys. Well, what's happening at those extreme heights is that all the normal cues you have available to you are just simply starting to go away, and you rely on the visual angle to estimate the size of the objects, which is not that accurate in this case. Okay, so there's that. I wanted to go through that. That's an important experiment. Okay, so you can see that once again, this is just more about the visual angle. Be aware of the size constancy equation, the size distance scaling equation. So all of those cues are important in establishing size constancy so as things get closer to us and as things move further away, if the size can remain constant, that keeps the world nice and regulated for us. The perception of an object size remains relatively constant, even if the retinal image changes. And this is the equation that's used to explain this is here. Size is equal to a constant, and then and it's based on the interaction of the retinal image size and the distance, perceived distance. If I have this information D, if I know the perceived distance, this interacts with the retinal image, and then I can judge the size. Okay. In the hallway and boring experiment, essentially, D has been removed. When you get rid of those cues, and when that happens, you rely mostly on the retinal image, and which is not going to be accurate all the time. Okay. Here are some slides about the visual illusions. Once again, I have some really good video clips that you should watch that really explain most of this anyway. So I'm not going to spend much time here on this, but a lot of these illusions, can happen because of some of the different size constancy mechanisms that we use. Essentially, it can work in certain situations, and in other situations they don't work. Or if we can utilize that, we can exploit those cues to create an illusion. All right. One of the more interesting ones, kind of jumping ahead here, I have There's the Ponzo. Here's an example here, the Ponzo illusion, which is, I also have a clip about this one. Here's linear perspective. So here, linear perspective makes us think the stuff here is further away than here. And this image, all right, this animal up here is the same size as the one down here. And I know this. I'm looking at this image right now. I intellectually know they're the same size, but boy, this one up here looks bigger. This is, once again, is consistent with the size distance equation. If I estimate D to be bigger here than here, both are producing the same R, the same retinal angle, but D is bigger. That makes that S number bigger. So so that's essentially what we have here. Very interesting. This size distance equation, it can in part be used to explain the illusion of the Ames room, amongst other things. Once again, I've got a great video clip that goes into this in more detail, so I want to spend too much time on this. But the Ames room is really interesting because the room is basically constructed in such a way as to trick you, to trick how far away you think these people are. It's really fascinating, and it uses some other cues to kind of trick you. So what's happening with the Ames room is essentially that normally the cues that inform us the proper size and distance of objects, or at least relatively close, they're used against us, and it creates the illusion essentially. And they're showing you here once again that there is and here you can see this is some of the explanations, but the video I have on the site is really much better, and you can see the room is structured in such a way as to trick you, to make you think that the people are in fact the same distance from you, but they're not, and it's fascinating how they do that. But that's the Ames room, so be sure to look through some of that, and you can see here I tend to favor the size distance scaling mechanism as a way to me is a pretty simple way to explain all of these illusions, but there's a lot of things probably going on here, and this doesn't explain everything, but you can look through that. There's relative size. Once again, this is more of a memory effect. We kind of know how big people are, and that can be used to trick us in this particular case. Also, I have another great video online as well about the moon illusion, so be aware of that one. This is really interesting. The moon does appear larger on the horizon than when it's higher in the sky. There's different explanations, but one I tend to like is the fact that the horizon is surrounded by depth cues. The moon higher isn't, and that can make once again, if I think that if the visual system is tricked into thinking that the moon on the horizon is in fact further away than the moon on the heavens, then the size is going to be bigger. Once again, R times D. That's just one theory, but that's not the only. Once again, the video clip I have, it really goes into that. Here's the so-called flattened heaven. The idea is that here, it might visually look like the moon is closer here than out here on the horizon, which would explain that. Once again, you have to understand that the moon, as it moves, as it's orbiting or whatever, the visual angle of the moon is more or less the same. Our author says it's the same. It's actually slightly different, but not enough to really amount to much. But that it's sort of fascinating there, and that's the moon illusion. We still don't quite know why. And finally, just a quick mention here: depth perception across species. I like to mention this. Humans have what are called frontally placed eyes, like the cat here, and we have overlapping visual fields. So you got the right eye here and the left eye. This overlapping visual field gives us excellent depth perception. All right, so we have evolved, like the cat, to have really good depth perception. Humans are basically predators, and in the sense that we hunt for, our ancestors hunted for food. We hunted for food, and our ancestors had to kill animals and such. They had to gather as well, and that requires depth perception. Here's a little rabbit going to run away from the wolf or whatever. Rabbits have really good panoramic vision, but they're without that overlapping eyes. Once again, by having the two eyes here, you get overlapping visual fields. You get more binocular disparity. Here, you don't have hardly any. They have excellent panoramic vision. This would be the rabbit, and that allows the animal to almost see. All it has to do is move its head a little bit either way, and it can pretty much see right behind itself, which is great because it tends to run away. And that'll happen if you have a little rabbit in your yard and you go out there. It's probably going to run. Of course, cats do that too, but rabbits are, they always seem rather nervous to me. But that's because it's instinctual. I would imagine that they're used to running away. Interestingly enough. And you can see what's interesting to me about depth perception across species. Once again, the different sense organs, the different nervous systems, they have a totally different world. You can see locusts use a lot of motion parallax to judge distance. What bats are really fascinating. They use echolocation. They actually use what would be a variant of our like an auditory type thing, to judge the distance. Like it's a sonar essentially. During World War II, we developed the United States developed sonar, which essentially mimicked how bats use sound waves to judge distances of objects and so forth. And here you can see and then an example of the bat. They can use their echolocation also to judge the size of objects. So their experience is quite different. Okay, well that was basically what I wanted to go through, and I hope this helped you know identify some of the major themes and concepts of the chapter. And I hope all of you have a great week. Take care.